To introduce myself, my name is Pance. I come from Macedonia. Currently, I work as a senior software engineer at Netcetera in Skopje. Besides my day job, I'm also the leader of the Java user group in Macedonia. I'm also one of the head administrators for the CodeFu algorithmic competition that we are making and organizing in Macedonia. And besides all that, in my free time, I like, well, to do a lot of hardware, and I'm also an IoT enthusiast. Me on the internet, you can visit my blog, pancha.mk. Hopefully it's online now. I just had my server fixed 1 week ago. And on Twitter, I'm Silomedos. I tweet every once in a while for some stuff there. So what am I going to talk to you about? My presentation is split into two pieces. So in the first half, I will concentrate more on talking about Raspberry Pis and its hardware aspects and a little bit more theory. Hopefully you will like it. You will need it definitely if you want to do hardware in the future in some time. And the second part, the more interesting part, is how to learn how to make your home smarter and get this starting boost into this whole section of Internet of Things. So just a fair warning before I start. I will talk about hardware. I mean, I will not go that much into that, but I presume that all of you here actually know how an LED works. You know, you just connect it and it blinks, that's it. So I will not explain that much into detail, but hopefully I will not get as far from the topic that I can. So let's jump right in. This is Raspberry Pi. Specifically, this is the Raspberry Pi Model 2, version 2, Model B, something, if they still keep on with the models. So short things about it, well, it's a pretty nice device. It's actually a single board computer. It has a 900 megahertz 4-core CPU, 1 gigabyte of RAM. It's based on this ARM v6, v7 instruction set architecture. From those things that actually make the device that popular and to be used as, well, a single board computer and to replace, I don't know, some stuff that you have at home, either for playing games or for network sharing or for media servers, stuff like that. It has hardware video support. It has HDMI output. It can output full HD without any problem. It has USB connectors. It has Ethernet connection. It has this audio connector there as well. Now, these things are not that interesting for me. I mean, this is just a regular computer. That's it. But you cannot make, just solely by combining these things, you cannot make the Raspberry Pi do something more interesting. So that's why the next three items. So first, it has GPIO headers. So GPIO stands for General Purpose Input Output. And a header is basically that you have an actual hardware header that you can connect devices to on. So here on the picture you can see these are these 40 straight out pins on the corner there. This is the Raspberry Pi GPIO header. Next, and what we are mostly interested here, is that the Raspberry Pi can run Java, and it can run JavaFX, and it can run supported Java. I mean, this is not like something like a port or anything like made solely to work for that, but it's actually supported. So both Oracle JDK and both OpenJDK can work supportably and performance-wise on the Raspberry Pi. And if you use the operating system that comes like recommended with the device, which is Raspbian in this case, you will get the JDK 8 bundle immediately. Now, as far as I saw with the last version, I think they're still stuck on JDK 1.8.0, so no updates there whatsoever. Yeah, but nevertheless, it works. So Java C, Java, they're already there, they're in the path, and everything is prepared. So, GPIO, yeah, that's interesting. Now, the GPIO here on the Raspberry Pi, on the second version of the Raspberry Pi, consists of 40 pins, where every single pin has its own designation and has its own purpose. The previous versions of the Raspberry Pi had 26 pins, and these 26 pins are the same as the first 26 pins that you're seeing here. So it's backward compatible. Now, as I said, every single pin out of these has its own purpose, and they are sort of grouped there. So there are groups of those, and you can see them. Well, I tried to guess the colors there. Yeah, they're good. So what you see here and what you see on the right side, actually, with the pins themselves, you can notice those groups immediately. So the red ones and the black ones are the powering, so we'll use that to power some external device that you will want to connect. The Raspberry Pi provides 5 volts and 3.3 volts depending on what sort of voltage you need for your device. Next, the green ones are the GPIO pins. Now these are general purpose input-output pins. They can work as an input or an output pin, and you can control them on bit level. From the other groups, you have the orange ones are UART, so that is basically the serial port connection. So I will just pass quickly through these. I will explain them later. Then you have the SPI, which are here. This is purple or pink, whatever. Then you have I2C, the blue ones, and the Raspberry Pi 2 comes with 2 additional pins for connecting it with an external EEPROM memory. I haven't worked with that, so I cannot share any details there. Now, this is the hardware part. But how can you actually control it? So you can connect something there. Well, I would recommend not to connect it directly, but use some cobbler cables and get it somewhere on the outside. But then how do you write software for that? So you can do software there on the Raspberry Pi in different languages, but we do Java here. So let's talk about Java on the Raspberry Pi. And specifically, when we're talking about Java on the Raspberry Pi and controlling hardware on the Raspberry Pi with Java, we're talking about the Pi4j library. So the Pi4j library, most simply put, is a GNI library to the underlying wiring Pi library written in C. So everything there that you will find about talking to the hardware aspects on the Raspberry Pi is based on this library, wiring Pi. Now the Pi4j library on its own side, it has these 2 aspects of working, these 2 modes of working. So it can work unmanaged, which is basically the translation from the wiring Pi library directly to Java methods, or it can work in its managed way, and that is the way that we're mostly used to, the more Java way, where we have factories, we have objects, we have classes, we have everything, we have dynamic collections and all these kind of things. But it's a bit slower. I will get to that a little bit more into detail. What you can do with the library is that actually you can control every single aspect of the GPIO header that you have there. So the GPIO pins, the green ones that I mentioned, you can control them, you can set them to work as an output pin or as an input pin, and you can do stuff with them. And also it supports the 3 interfaces that are already provided there. So it has this out-of-the-box support for SPI, for I2C, and for UART. Again, it has managed and unmanaged access, and if you go to the project page on GitHub, you will see that besides the package that is there for the Pi4j core, there are also a lot of extension packages. So these are the exact software that you need to use if you want to connect a specific device for which, well, the software is already being made. So no need to reinvent the wheel there. Okay, enough talking. Let me show you some examples. So this is the hello world in the hardware world, yeah. So to make the very, very, very hard task of having one LED and to make it blink, to make it turn on, that's very heavy. So what do you have here? You can see on the right side, so this is a Pro board. Again, I will not explain those things. So basically what you need to do here is you take 1 pin of the GPIO header, and as I said, I'm not connecting that directly to the Raspberry Pi because there are severe risk for short-circuiting it, and we are breaking it immediately. So yeah, use a cobbler device or something like that connected to a proto board and work there. So what you need to do here is actually take 1 pin, connect the LED through a resistor in order not to blow it, and ground it on the other side. And then in the code, we need to simply control that pin. So what we do with Pi4j, again, this is the managed way to access, this is the Java way to access. So you see that we have GPIO factory, we're getting the instance, and this is basically the controller, the GPIO controller. Everything else from that point on, we're doing with it. So from the controller, we say, okay, now we will take 1 pin and we will provision it, we will export it, we will configure that pin to work as an output 1. So here we take the GPIO 00, that is the software designation for the pin, and we mark it as digital output pin. And since it's a digital output pin, we immediately need to set it to be either on high or on low. This is on high. Then what we do, okay, this thread will sleep for 5 seconds, then we'll take the pin again and we'll drop it down on low. So these high and low levels actually mean that we control the voltage on that pin. High level means 3.3 volts. Low level means 0 volts. And at the end, just to collect the garbage that is left behind us, we execute GPIO shutdown. So what this does is actually you start the program, it initializes the pin, it sets it on high, and effectively the LED goes on, blinks. Then for 5 seconds, it is on, and after 5 seconds, we drop down the pin to a low state, and the LED gets turned off. That's it. Next. Now that was the hello world in order to represent something. Now what's up world? Now let's try to communicate something with the outside. So let's try to sense something. And the most simple thing that we can sense is a tester. We have a tester, we click it, let's sense that precise moment when we've actually clicked it. So you see similar schematics there on the right side. So what is added here is that now I've taken another pin and I've connected the tester to it through a pull-down resistor that goes directly on the ground. And the code is a little bit enriched here. So you see that besides the provisioned digital output pin, which is the same as in the previous example, now we have provisioned digital input pin, which its software designation is GPIO 01. And since it's an input pin, we need to define at the moment it is pulled down or pulled up. This one is pulled down here. So in order to control that, in order to configure, in order to program something to happen at that precise moment when you will click on the tester, you simply bind a listener at that pin. Here I'm using Java 8 syntax, so you can see that to the pin in, I'm adding a listener, that's an event, and what I'm checking simply is that whether at that moment when the event has occurred, I'm getting the state. This is the input state of the pin. Because this event will actually trigger on every moment when you click or when you unclick the pin. So I only need to track those points when I'm clicking the pin, so when the pin is down. So what I'm doing here, I'm simply checking what the state is, and if the pin is down, then what I do is I say pin out toggle. So basically what this thing does, every time when you press the tester, the LED will go on, then the next time when you press it, it will go off, then the next time you press it, it will go on, and etc., 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 etc. But this is all good if you want just to waste your time with LEDs at home. But if you want to make something really productive and if you want to make some extensions for the Raspberry Pi or for any other device out there that can be programmed, you need to go with something else. So you need to think in terms of modules. And you need to think in terms of communicating with the modules. And that's the exact way in order how to make extensions there. So here I will try to explain the three most common interfaces that you can find in every programmable circuits out there, including the Raspberry Pi and some other ones that I can talk to. What is the logic, the basic logic behind them, and how can you communicate with them? So the first one that I want to mention is the UART, or we all know it as the serial communication, the good old serial communication. So it's the most simple protocol that you can use. It's based solely on two pins. You have a transmitting pin, you have a receiving pin. And in order to connect the module, you take the transmitting pin, connect it to the receiving pin on the module, and vice versa on the other side. What you need to do at the beginning, as every serial communication, you need to define the baud rate, i.e. the speed of the communication, and to define the data frame if you need it, if you're not using the standard one. So that is the data, the stop, and the parity bits that are included. How can this be done in code? Well, this is the Py4j implementation, but nevertheless, every implementation that you can get out there more or less follows the same principle. So first, you're creating an instance of the serial object from the serial factory here. You add a listener to it. That listener will basically be the event handler that will get triggered every single time when you will receive data from the module to your device, to the Raspberry Pi. Then the next thing we do, you open the serial connection. You see here we have a default COM port. This is actually the serial port on the GPIO header that I talked about. And you define the speed. It's 115,000 bits per second. And in order to send data from the Raspberry Pi to the device, you simply write a string in the same manner as you're writing a string to a console output. That's it. So here we have serial write line hello from Raspi. So what will happen here is that you will activate this piece of code. It will open the serial connection and it will say hi from Raspberry Pi. And if the device that you're connecting to it says hi back, then this hi back will be transferred back. The listener will get triggered and you will get on the standard output, you will get this hi back printed out. Just that simple. But the serial port is way slow, it's not that much reliable, and yeah, explicably you cannot find it at every single module that you can put your hands on. Next interface that I want to mention is the SPI, or it's an abbreviation for Serial Peripheral Interface. This interface is also known as the 4-wire communication, based that we're using 4 wires here. So these lines here means the first one is clock, SPI clock. The second one is master output slave input. The third one is master input slave output. And the fourth one is slave select. So what basically we have here, a clocking signal, output lane, input lane, and slave enable lane. So why is this actually made like this? Now the SPI is intended, it is designed to work in this master-slave situation, master-slave configuration, yeah. So the master in our case is the Raspberry Pi. It is the one that dictates everything, and the slave is the targeted device that we're communicating with. every data that we're sending goes through the MOSI pin, every data that we're receiving goes through the MISO pin. Now what makes the SPI used and helpful in that manner is that it's very fast. Now compared with the serial communication, it goes through some speeds of in the area of megahertz, and it's full duplex. Now this full duplex is a bit tricky, because here you need to go with the rule, if you want to receive something, first you need to send something. So explain that simply, it's like if you need to receive some data from the device, but just to receive something, nothing more, then you need to prepare a buffer on your side, fill it in with some garbage, and then send that garbage to the device, and the device will fill that back. So basically the communication here goes like swapping two buffers, and that's all. That's even notable here in the code. So again, this is the Pi4j implementation. Now, this is not the Pi4j managed implementation, solely because the communication here is done very fast. And in my experience, I wasn't able to tune down, the managed implementation to go nice. So I got some lost communication there. So as you see, the communication here is rather simple. So we just do a wiring pi setup, then we set up the SPI, we set which channel is it and which speed is. Now, the Raspberry Pi has 2 channels. That's why actually this is here. And at the end, we're just making this communication. So as I said, this is a full duplex communication. So there's only one line of code that you need to write either when you're sending data or when you're receiving data, and that's it. And the data that you're sending or receiving is in the buffer, or it will be placed afterwards in the buffer. Yeah, that's very interesting. Okay, and the final interface that I want just to mention, and one of my favorites actually, is the I2C. Or you can find, it's the same interface with different abbreviations. You can find it as I2C, IIC, and all of those means for inter-integrated circuit. Again, this is a serial interface, but what makes it special is that it's addressable. And that is quite nicely. It's also a simple interface in terms of pins. It only needs 2 pins, so SDA and SCL. This is the data line and the clock line. And since it's addressable, you can use those 2 pins and you can attach multiple devices on it. So you need just one interface and you can attach as much as you want. Well, not as much as you want, but as much as the addressing space can actually allow you. The communication is very similar to a serial communication, except that again we're using some sort of buffers here. It's a simplex communication. We're writing and we're reading data explicitly here. So this write buffer, this read buffer, that's all. And the only difficult thing that you can encounter at the beginning is what is the address of the device that you're communicating with. So you will attach the device, but you cannot actually communicate with it if you do not first initialize it with its own address. Now usually it's up to the manufacturers of these modules that they provide, and they will need to tell you, okay, now the address for this device is this and this. But they kind of seem to forget this. I don't know why. But nevertheless, there is a tool for that. So there is a command line tool called I2C Discover. You can run it from the command line, and what it will do, it will simply scan the entire address space on the I2C connection, and wherever it will find a device, it will simply say, on this address, there is something. It has no idea what it is, but there is something. It will be up to you to decide, okay, this is probably my device, because I only have one device here attached. Now, some devices may have multiple addresses, blah, 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 but yeah, let's not hold on to that. So again, enough talking. Let me show you some example. This is a NFC module based on the PN532 chip. It's manufactured by this company IT Studios. I believe they're based in China, not really sure. So what it does, it's a regular NFC module. It allows you to read from NFC tags, to read the ID, to read the payload that you have inside, or even to store the payload that they can have inside. It works with the most common NFC tags that you have encountered so far. Now, the chip itself supports these 3 interfaces that I mentioned. It supports SPI, it supports I2C, and it supports UART. But the reason why I chose to explain this device, this module actually, is because of the way that you can connect it. So if you see there on the corner, you can see that there are 26 pins. And these are the same layout pins as on the Raspberry Pi. So in order to connect it to the Raspberry Pi, you just take a 26-pin cobbler cable and you connect it directly. And that's it. But, however, the designers here made some, they made some trade-offs. As I said, the chip itself supports 3 interfaces, but these 3 interfaces cannot be directly passed to the GPIO directly. So what they did here is that this header, so the Raspberry Pi header, only supports SPI. So in order to make the communication, you need to make the communication in SPI. If you want to do it into something else, you need to a bit hack the design in the background, so add some wires or whatnot. So what do we need to code in order to make this work? Now this is the tough one. I will not explain this. I will definitely not explain this. But this is actually the hard part of writing code in the embedded area. Because quite often, if not even always, the communication is very strict. It follows strict byte rules. It contains preambles, postambles. It contains a lot of operations. It contains checksums every once in a while. And in order to make it reliable, we need also to send these acknowledgement signals back. So here's actually how it looks, one simple cycle of communicating to an NFC module. So the first part is we need to send data. We need to send a command. And this command is basically read me the ID of the NFC tag. Now this command, read me the ID, is stored in the body. And that's there. But you can see there's a lot of stuff just simply that is wrapped around. And you need to send that stuff along if you want to make the communication to work. Then you send the data, and if everything is fine, you will receive an acknowledgement from the channel back. And that acknowledgement is always the same 6 bytes, so you need to compare if everything is fine. If it's not fine, then you need to simply resend the data. If it's fine, then the next thing that you will receive is the actual read response. And again, here we're only interested into the response. You can see it there. But besides the response, we will get also all these frames and garbage that we don't really need. But again, we need to check it just to make sure that the communication has went well. How does this look like? Well, that's it actually here. This is one NFC device that I've made. I will just play it down. So you can see the architecture, the software one. I do not want to get into details because I can talk like half an hour solely for that. The source code along with the instructions in order to make this device at home is already there on GitHub. So go on my channel there, Salamadus is DoorNFX, or just search for it and you will see it. The thing on the right is a video. I will play it right now. Just pay attention to several details. So you will see the UI on the screen. On the left side, you can see the NFC module, and you will see that on the start, I'm actually bringing the tag there. And on the right, you can see an LED. Now this LED, imagine the LED as a door that opens or closes. So I couldn't record a door here. Okay, so how does it actually works? First, we take the tag. Now we're prompted for an input ID, and if it's correct, then it says granted. And you see the LED goes green, which says, yay, you can come in. Now the second time, I'm entering a different pin, which obviously is the wrong one, and I'm trying to enter, and it says, no, it's forbidden. So yay, that much work solely to make this thing here. But I was talking solely about hardware, and now here I'm presenting even user interface. So where did this thing actually came from? And it's a touch screen, and it's working, so what's up with that? Well, what you actually saw there is a JavaFX interface, a touchable JavaFX interface, if you will. If you want to make something like that on your own, so I will not explain the details of JavaFX, because again, 1 hour more, stuff like that. If you want to give it a try with JavaFX, what you need to do is follow these steps. So first is acquire PiTFT, or don't. Now the PiTFT is the screen actually that you saw there, and it's touch screen, and it's directly attached on top of the Raspberry Pi, connected on the GPIO header that I explained. But nevertheless, you can code JavaFX in the same manner for the regular monitor that you will attach to your Raspberry Pi, except that it will not be a touch screen. That's it. Now the second step here is scratched, and it's scratched with a big reason. So initially when the JDK 8 was promoted, and it was said that it will go now from this version, from the version 8, it will go shipped to JavaFX 8, and it will be supported on all platforms out there. Well, it's not anymore supported on all platforms out there. So from one version, actually Oracle decided to drop the support for the ARM JDK, solely for the ARM JDK. On the standard edition, it still goes shipped all together, but here it's simply no longer present. I really don't want to get into the insight of why this decision was made. Turned out that it was sort of a port, but nevertheless I was firstly furious because it was actually a very nice setup. It was working fine. But lately I'm even happy that they made this choice. Because with that choice actually they gave the opportunity for the OpenJFX to rise even higher. And what from Oracle did, at least what I think they did, is that they took all the changes that they have made and they committed it to the repository for the OpenJFX. Now, I'm not sure if that actually happened. I was simply told that that actually happened. So, step 2.5, ignore the JavaFX built into the ARM JDK8 because it's no longer there, and download your binaries manually. Now, this is a bit of a tricky step because there isn't any official site where you can download the binaries directly. So you can download the source code and you can build it on your machine, but that will take time, it will take skills, and it can get you frustrated a bit. So the most reliable source that I found for already pre-compiled, pre-made, pre-built binaries is on that site on the bottom. It's an IP, it doesn't even have a domain name. But nevertheless, one guy has made that, it has nightly builds, and you're getting fresh binaries there every day. It's working perfectly fine. I worked on that, I had no problems whatsoever. Then the next thing what you need to do, build your project, obviously. And when you execute it, here is the biggest trick. So you see all these parameters that I'm adding here. So the first one says use an external directory, and this one says do not use the JavaFX if it's already present in the ARM JDK if you're using an older one, but take the OpenJFX. So this is the directory to the JFX/ext folder that you have in the binary distribution of OpenJFX. The next parameter that you need to pass here is to use the Monocle platform. This is very important. The Monocle platform is actually the implementation of JavaFX. It's windowing toolkit for embedded systems. And these kind of embedded systems that do not have or may not have at the moment a graphical user interface. So that is definitely what you need. And the two parameters on the second row are actually the stuff that I've added and what you will need also to add if you want to make the UI to be displayed on the touch screen. So what happens actually here is the OpenJFX and JavaFX for that matter, they do not need any underlying X windowing system or something like that, so they just take a frame buffer and they render everything on it. So if you need to connect to an external display, you need to link it to its frame buffer. And now the touch screen here is the FB1. The HDMI output is actually the FB0. So here I'm just routing it to the FB1. And the last thing is use software rendering, because there is no hardware support for rendering there. So that's actually it in order to run it, but just be careful. The resolution here is very small, so it's 320 to 240, yeah? And be cautious. You have software rendering, you have limited stuff, so you cannot really do 3D projections or something like that. You cannot run Doom on it, I think. So, I'm talking about all that, but what about the second part? I mean, I promised you that I will explain about home automation, making home smarter or everything. So what do we need to do? Should we just buy 10 Raspberry Pis and connect it to different places at our home and configure them, each one of them, to work in its own manner? Well, yeah, you can do that, but first it will cost you. Second, it will be very hard to do. Third, it will be even harder to maintain. And yeah, for why even bother? Because, well, you have some other options. Speaking of that, let me introduce you to the wonderful world of ESP8266. Or, in my case, what I'm using, the Node MCU Dev Kit. So, the device that you see on the side is called Node MCU Dev Kit, Development Kit. It's basically a development and prototyping board. Very, very, very similar to what you have seen in the Arduino world. So, the Arduino is, again, a development prototyping board which is based on the 80 mega integrated circuit. This thing, merely the same, but is based on this ESP12 chip, or ESP12E if you use the last version. What this chip actually does, it's same as the Arduino, it's fully programmable. It wasn't made like that at the beginning, it was made just simply like a standalone device, but now you can actually code completely on it, you can do whatever you want with it. From the interfaces that it can support to connect to other devices, similar as to the Raspberry Pi and very similar as to the Arduino. It has GPIO pins, which again you can control as input-output digital pins. It has UART, it has SPI. Now it doesn't have I2C, at least the current versions don't have I2C. It doesn't have PWM, and it only has one analog input. So that is if you want to see a short comparison compared with the Arduino, for example. But on the other hand, it's faster. It runs on 80 megahertz clock, and the killer features that actually make it so popular is, first, it has built-in Wi-Fi. So what you can see here, actually, the device, no. Yeah. So the device actually, the entire board is the prototyping board. This is the chip. This is what we need. This is the entire core of it. And what you can see here, this is an antenna. So this is the integrated Wi-Fi antenna there. So the Wi-Fi there is built in, and it's quite reliable, actually, I can say. So it supports all the major protocols. It can connect to unsecured or secured networks. And, well, besides the speed that cannot be guaranteed, apart from that, everything seems to be working fine. Next killer feature is that this device is very low on power consumption. So you can run it on 2A batteries, 2 or 3 or 4, whatever. But nevertheless, you can just combine it with the battery, just leave it aside, and it will work. And it will not waste that much energy. So I presume that with one setup, if you keep down even to standby positions or something like that, you can make it work for 3 or 4 months untouched, and it will do its trick quite well. And the last thing is, it costs only $5. And the $5 is for the development kit, the total one. The device only, you can, I believe you can find it for $3 as well. Yeah, for wholesale offers, you can even find it for cheaper. So this is the hardware part, but what about coding? How can you actually code on that? So you can code in few ways on the ESP, but the way that I support, and which is the recent one, and well, which is the easiest and also the mostly supported with a lot of features, is to use the available Arduino port. It's like 4 or 5 months ago, I don't know, the Arduino community came out with this huge announcement that they now support the Arduino IDE, the Arduino SDK, alongside with the programming language, to be used for coding on the ESP. And that was a great news. That was really a game changer. Because the Arduino community is huge, libraries there are a lot, and the ESP actually offers features that the Arduino simply cannot handle. So what you can do with the ESP, besides coding it as a regular embedded stuff, doing stuff, you can make it work either as an access point, so that means to start a software access point, and it will broadcast its own network to which you can connect to, or you can make it to connect to an existing Wi-Fi network that is already present. After that, when the connection is being made, you can, well, yeah, you can do whatever you want with it, but in order to make it useful, you will most probably want to work with some of the offered libraries that are out there. So the first one is the web server, or the advanced web server. So what you can do with that, you can actually install and you can configure an HTTP web server that will run on this device. Now, do not expect springy stuff there or something like that. You have a simple HTTP server. So it will display HTMLs. You can attach handlers to some specific addresses of it. It can respond to these addresses. It can take data. It can post data back. Everything that, well, yeah, that you can do with a simple HTTP server without using any programming language beside. You can use it as a WebSocket client or as a WebSocket server. Or you can connect it to some third-party devices, like, so you can use the NeoPixel bus. This is the library for working with these Adafruit NeoPixels, which are basically RGB LED diodes. They're also known by WS2812. I have an example of those, actually, I'll show you. And DHT11, this is a temperature and humidity sensor. It's one of the mostly used. There's also DHT22, yeah. There's already a library for that, so you do not really need to reinvent the wheel. You can just use it out there, connect it, and everything will work. So again, one short example. This example is how you can actually use an ESP device as a standalone tool, as a standalone device, yeah. What I did here is that I made a wirelessly controlled light. And it's not only turned on and turned off, but you can also choose the color of it, yeah. What you need here is an Node MCU. I've used the 0.9 version. You can use the 1.0 version. That really doesn't matter here. And you need one RGB LED strip. It has to be WS2812, or if you buy it from Adafruit, they have their own brand for that. It's called NeoPixel. The code itself, what it does, it starts, first it connects to a network, an existing network. If you can see here on the picture, it's actually my phone broadcasting its own network. It has a hotspot. So the device first connects to a network, then starts up this advanced web server. It shows the root UI when you connect to it, and it handles the requests. And the requests actually are done by adding links to, well, this awesome user interface that you see here. So it's very hard, I mean, to not determine what these buttons actually use there. So the code for this and the instructions of how to make it, I've already open sourced it. It's already there, so just visit my blog. This is not on GitHub, because it's just one file. That's it. Visit my blog. You have the instructions there. You have the source code there. It's quite enough to get you started by working with DSPs on the Arduino SDK and everything related that you will need. But still, this is nice. It works. It links. It lights. You can change the color. But again, this is a standalone device. This has nothing to do with Internet of Things. It has nothing to do with home automation or smart home or whatever. So for that, I introduce to you CHECHE. So I don't know if here in Serbia this word is actually used. I don't know if in Macedonia is actually used that much. So CHECHE basically means a thingy, a small thingy. What I wanted to do here with this project is that on the one side, I wanted to make cheap nodes, all these connected nodes, each one of them with a specific purpose. The medium, which they use in order to connect, in order to be actually Internet of Things, to be connected there, is by Wi-Fi. Third, really every single person needs to be able to use them, needs to be able to buy them, like, I don't know, and to configure them without any hassle whatsoever. So they need to be really easily configurable by the end user. The physical UI that they provide needs to be very simple, and it needs to be quite intuitive. So what I used here is that I have one status LED, just to say whether or not it's working or not, and I have a restart button if something goes wrong, in order to reset the device to its initial state. Now next, this is one of the key stuff that was also presented yesterday at the keynote, is that in this area a lot of stuff can and will definitely go wrong. So whatever you do, whatever you design, both in hardware-wise and in software-wise, you need to be made sure that it will be very, very robust. So think about every single piece of code, every single wire that is outside. At one point, it will fail. And you need to think of a mechanism in order how to cope with that error at the end. So the code that you need to do needs to be very robust. It needs to know that it can disconnect from the network. The server may go down. Simply, the connection can be interrupted for any sort of reasons, and you cannot just froze there and not try to do anything afterwards. So it definitely needs to be robust. It uses WebSockets for communication. It has this self-describing initial info protocol. So basically, when I'm turning on the device says hi to the server and explains itself to the server. It says, hi, I'm an LED. So if you want to communicate with me, just simply send me this data and send me the color and I will blink, or something like that. If it's a switch, then just tell me that when I need to turn on or turn off, and that's it. And the final piece, this is the other side, they need to be registered and controlled by a home mini server, or the other side, if you do not want a home mini server, to be easily connectable to a cloud application there. The first thing, the use case of how to configure this is, so initially you fire up the device. The device says, okay, this is the first time when I'm started up, I need to be configured. So what it does, it broadcasts its own network. And then you just simply take your iPhone or take your smartphone, connect to the network, open this IP. It's still with a fixed IP, and it's always that IP. I still haven't managed a way how to translate this into a name or something. And there you can configure it. So what you actually enter there is the device name. So let it say Svetilka, something. You put the SSID and the password of the network that it needs to connect to. So this is actually your home network. And the hub location. This is the location of the server. This can be an IP address. This can be a domain name. Last but not least, you can set a mode. So again, as I said, I'm just maintaining one code base, and it can work in several modes. So let's say that the first one that we will configure will be a light. Now, if we submit all that, then this data will be permanently written onto the EEPROM, and the next time when the device will reboot, it will start with these settings. If you change, let's say, the password of your home network, you just simply click on the restart button at the device. It will return it back to factory defaults, and you can configure it all over again. So that's really not a problem. Now, the other side is the server. So here, this is my home mini server, what I've made, but it definitely doesn't need to be limited solely on that. Now, the protocol is quite easy. It uses WebSockets, so whatever you can do with WebSockets, you can simply replace it as your own server. My home mini server, which I have made, which I will present here, is, again, consisted of Raspberry Pi 2 plus with the Pi TFT. I'm running this Adafruit patch Raspbian OS, so there I do not bother with the driver for the touchscreen and everything. It's already there. I'm using Java 8 alongside with OpenJFX, and in order to keep things as simple as possible, in order to make a WebSocket communication, I'm using this Java WebSocket library. That's all. Now for this, I don't have any source code yet. The reason is to be honest, I don't know actually what to do with this still. Should I just open it, or I don't know, can I actually earn enough for a new car for this? I don't know. I'm still thinking on the subject, so yeah. So enough talking, I will show you some demos here. These demos, as you can see, are professionally recorded with my smartphone camera. So I want to just explain a few stuffs at the beginning. So you can see the node MCU there. It is the core of the system. There is an LED there somewhere in between. You can see it actually blinking. So when you turn off, it will go on. When it's connecting, it will start blinking. When it's connected, it will always be on. That's it. And for every device here that I will present, it has some other stuff connected to it. Here, this is a light. So again, we have these WS RGB LEDs connected to it. And on the right side is actually my home server, so the thing based on JavaFX. So, yeah, let's see. First, I'm firing up the device. Pay attention to the LED. It will start blinking. So that means it is connecting. Now it's connected, and it's saying hi to the server, and that's it. The server is here. And now let's try to control it. So click it, open it. This is actually the interface that is being told by the device itself. So let's change the color. Here's the color. Let's change it again. A different color. Let's change it again. Something whitey. Let's change it again. Blue. At least a variant of blue. Black effectively means turn it off. Yeah, the touch screen is not that reliable. So again, just change it back to blue, then go back to the menu, and you can see that the last state is actually remembered here. So you just need to see the dashboard, and you will see what the current color of your light is, if it's in a different room, let's say. On the left side, you can see the connection, so it's nothing specific. You have the status LED, the reset switch, and the connection directly to the WS RGB LED strip. The next example I want to show you is a relay switch node. So it's again firing up, connecting, and there it is. It's connected. It says, hi, I'm a switch. I will just need a button. And you toggle that button, and you can see on the middle there on the proto board, that's a relay. So now to make things simple, I've just simply attached an LED to the other side of the relay. But if you make if you take a powerful enough relay out there, you can, I don't know, attach a stove on it, and you can control it remotely, or a heating element, and you can control it remotely without any problem. And if you manage to see, again, on the dashboard, you can see the state of it. So if the button is green, meaning that it's currently turned on. If the button is red, meaning that it's currently turned off. The scheme, again, is very simple. So we're just connecting to a relay, which is communicating to the LED. And that's it. Next example. Let's read some input data here. So this is a temperature, humidity, and light sensor. It's based on the DHT11 sensor. You can see that blue piece there. It has also a light resistor. It's not really noticeable. It's on the top left corner there. And everything else is still the same. So what this does is it has no input, it has no output direct, but it has just a broadcasting capability. Again, firing it up, connecting. Says, hi, I'm a sensor. I will simply broadcast some data to you every once in a while. So there it is, sensors. You just click it here and wait for the first broadcast to be here. So yeah, 24 degrees and 38% humidity. So you go back on the screen. So I initially had one more example here. This was the device sensor node, but unfortunately my sensor broke there, so I wasn't able to finish it. It's still here in theory. I mean, I've done that with an Arduino. So idea is that actually a socket adapter that you can use at home and detect whether or not the device that it's attached on it, it's currently on. So the basic use case will be you go every morning at work, and halfway there you say, oh, did I turn on my stove on? Is my oven still on? So you just take out your phone and you can see it there. The data will be still present. So, to conclude, JDK 8 alongside with OpenJFX is pretty much running very smoothly on the Raspberry Pi 2. I was quite amazed by the performance of it compared to the previous mocked implementation that we had to use alongside with FBCP and some other utilities out there. This thing is working perfectly fine, and OpenJFX is doing its job quite well. So I honestly tell you, give it a try. It's good. You don't really need a touch screen or anything, for that matter. You can just take a Raspberry Pi, connect it to a monitor, keyboard, mouse, and write down a JavaFX code. That'll be it. The second thing, the ESP8266 and everything around it is a huge game changer in the maker communities. I mean, it's a real boom. It's all like 1 year and a month, I think. And it's pretty, yeah, it's still not mature that much, but nevertheless, the community grew a lot. There are a lot of examples there. It's very cheap. You can buy it, let's say Amazon, let's say eBay, let's say these Chinese websites that there are. It's everywhere, basically. Take one of them, buy it, and start hacking. So there are instructions everywhere there on the net. Last but not least, really be careful. So here you are coding for embedded environments. This is really not your desktop i7 PC. It has limits. You cannot go past these limits. If you want this thing, I don't know, to attach an ESP and you want to, I don't know, recognize a face, you will fail, because simply that is not made for that. So just be careful about that. So, yeah, that was everything actually that I had to say. I'm now open for questions, and if someone wants to see these things, so I have them here in this box. Of course, they're offline. I'm not trying to power them on right now, but if you're interested about the hardware and everything, you can just approach me here after the presentation. I will tell you anything about it. So again, thanks for listening. I'm Pance. You can find me on the internet here. So I'm taking questions. Any questions? Yeah. Can Java work on Arduino? No, but actually I've seen some experiments with it. Again, it's not Java, but it's transcoded Java, I think. Now, if you're talking also about Java micro edition here, I really don't know. I do not have the answer. I know that it's being made with a very low footprint, and it can work on embedded devices, but if it's possible for the Arduino, I have no idea. Anyone else? Yeah. No. So the question is the interface that we saw actually from where does it come? Is it on a web browser or is it something else? So no, it's not from a web browser. This is the interface that is being produced by JavaFX. So in order to make it, in order to show it, you do not need anything else except command line. That's it. So as I said, when JavaFX starts up, it connects directly to the frame buffer, so that basically means directly to the device, and renders its user interface there. It needs nothing else. It doesn't even need X windowing system, none whatsoever.
But information with which type of device, how it is getting that?
Okay.
How it is getting information which kind of devices?
Okay, so this is in one. This is here, this line. So I'm saying self-describing. So it's up to the device. In the period of handshaking, it sends this JSON data, and there it actually says everything. My name is this and this. I'm programmed to work in this and this. So I expect these kind of input messages. I will send you these kind of output messages, and eventually I will broadcast some data to you. That's all. There.
How do you execute jar files on RaspberryPi?
Okay, so where was it? So you take this, you place sudo Java, always use sudo Java, because if you want to use hardware aspects of the device without sudo, you cannot actually access that. Sudo Java, and at the end, your jar file.
So you are connecting Pi to a monitor and a keyboard, and you execute that command?
Nope, I'm accessing it through SSH. And from SSH, you can execute it. Yeah. As I said, you don't need any graphical user interface. Yeah. Yeah.
Okay, without any internal storage.
Mm-hmm.
Okay, how much is left for any kind of application? How much JDK is carrying?
Okay, but here you're talking about the storage of the device. So
when you run a program,
okay.
Okay, you have to run Java also.
Mm-hmm.
Yeah. So how much is left for the application per se?
Mm-hmm. Well, exact number here. So the question is how much of the memory is left for the application, considering that we run JVM and everything. Yeah, Arduino has in kilobytes of RAM. So the Raspberry Pi has 1 GB of RAM. That's it. Initially, even if you want to start an interface on it, you need to be aware that there will be some memory splitting from which a part of your RAM will be reserved solely for the graphics adapter. So let's say 256 megabytes or 128. That is actually the minimum value there. Everything else is for applications only. So exact number, I don't know what to tell you here, but if you do above 500 megabytes of RAM, you're definitely doing it wrong. Yeah. Everything else actually remains for that. You have no other processes except, well, the basic ones that keep the operating system running. Everything besides, it's turned off. Okay, anyone else? Yeah, one more.
You can put the SD card and
Yeah.
make such file and make more.
Yeah, that's from the operating system, yeah. But it will be terribly slow, so don't do it. Really, don't do it. Yeah, yeah. Okay, so thanks everyone for watching. I hope you enjoyed the show.